Hello. Inspired by Ben Ita's video series about an 8-bit CPU on breadboards, I built my own version. I made some enhancements to Ben's original design, and in this video I want to talk about the enhancements on the control logic and the reset cycle, and I want to explain how my new introduced interrupt function works. I believe if you're watching this video, you're already familiar with the concept of a control line in a CPU, but I want to do a small recap so that we are all at a similar level of knowledge. So let's say the control lines select the low-level operations in a CPU. That means, for example, write a value to a register or enable a register output so that the content of the register is visible on the data bus. Such operations may be more complex, like an ALU function, so that a combination of control lines decide whether an ALU is adding or subtracting. Instructions are a combination of active control lines. So an instruction may be, for example, move register B to register A, and to accomplish that instruction there are two control lines that have to be active at the same time, which in this case are the BE, so register B enable to output, the register B content is visible on the data bus, and register A write content, so that the register A takes the content from data bus and writes this data into the register. So there is a mapping between an instruction and the control lines that are active for this instruction, and this mapping is programmed into a programmer read-only memory so that the active control lines can be derived from the active instruction. And this is done by setting the input to the EEPROM, say the address lines, to the instruction code, and the output of that EEPROM, say the data lines, are the active control lines. So you can simplify this like this, that you say there is instruction register, and in that instruction register you load the active instruction, and that instruction register drives the address lines of an EEPROM, and the data lines, so the output of that EEPROM, tells which control lines are active. And you don't have to have just one EEPROM, you can have more of those, so all of those will have the same address line set, but have different control lines triggered. Some of the instructions have more than just one step, so there is more than just one thing to do during that instruction. For say, the instruction add register B to register A consists of several steps, where the first step is enabling the output of register A and loading it into the accumulator, so in the ALU. Step 2 will be enabling the output of register B to the data bus and add the value of the ALU to the value on the data bus, and also latch the flags so that we later know whether there was a zero flag or a negative event. And the third step, of course, is moving the new value into the A register, so we enable the output of the ALU and load that value into the A register. Those multi-step instructions require an additional step counter so that we can say which instructions have which step, and that step counter is just added to the lines of to the address lines of the EEPROM, so that the address lines are set by the current instruction and the current step of the instruction. So the step counter counts up every clock cycle. So whenever a new clock cycle begins, the step counter counts up and so walks through all the steps that belong to an instruction. And on the other hand, it has to be reset to 0 whenever a new instruction is fetched, so that for a new instruction, the step counter starts at the beginning. Some instructions are conditional. That means what the instruction does is dependent on, let's say, the state of a flag. So let's say there is an instruction called jump on carry set to address 8, and this instruction shall only change the program counter if and only if the C flag is set. So that means if C is set, change the program counter, and if not, don't do it. So these are two different ways to execute the same instruction depending on whether or not the C flag is set. And you can see that the control lines that we need are dependent on the flags, so on the state of the flags. And to do that, you can also connect the flag register to the EEPROM. Let's say there is a third input to the EEPROM beneath the instruction register and the step counter. Also the flags go into the address lines and so decide which control lines are active. All that put together leads to Ben Eater's design. I have a more simplified version of that design here on my screen. There are the flags, which are two flags in Ben Eater's case, which is the 0 flag and the C, the carry flag. Those are 2 bits of the address lines. Then there is the instruction register, where in Ben Eater's design there's only a 4-bit instruction, say 16 different instructions. So there are another 4 bits for the EEPROM, and there are 3 bits from the step counter. While the step counter has 4 bits in total, Ben Eater only uses 5 steps of that step counter. So in total, that makes 9 bits of address lines for the EEPROM, and in total he has 16-bit or 16 different control lines. So there are some drawbacks of Ben Eater's design, and one of the problems is that there is a fixed step length. So no matter how many steps an instruction really needs, you always have to have 5 steps, and that means there might be empty cycles in an instruction, slowing down the speed of the CPU in total. And the other thing is that the flags and the instruction register change at the rising clock, and the step counter changes at the falling clock. And that means that there is no stable time for the address lines during up or down clock, and that might lead to problems if a control line changes during the high time of the clock. So I changed that design a bit. So in my design, the control logic only has a 12-bit step counter that drives all the address lines of the EEPROM. So this is more simple on the first look. It's getting more complicated later, but on the first look, it's easier to have just one step counter, and that step counter is able to address the whole microcode EEPROM. And in my case, I have 32 bits of output, so there are 32 control lines. And you see there is a 12-bit input to that step counter, and so that step counter can be loaded. Usually it counts up by default, so whenever the falling edge of the system clock appears and there is no other demand, the step counter counts up, so gets to the next step of an instruction. To operate the control logic, I added two new control lines, whereas the first one is IC, and that control line is active on the last step of every instruction and tells the control logic to return to the fetch cycle. So this is to prevent any empty cycles in an instruction. And the other control line is the IL line, which instructs the microstep counter to load a new value. If you see that in the schematic, you first might notice this unnecessarily complex thing is nothing but an AND gate built out of 3 spare NOT gates and an already available OR gate, but I didn't have an AND gate available in the area that I was building that, so I set it up like this. And the output of this gate will always be 0 as soon as one of those control lines, IL or IC, are active, because they are active negative. And those control lines are fed into this HCT161 counter chip. And since the load line is active negative, while the count enable line is active positive, the counter will always either load or count, and it will always count up if none of those control lines is active, and it will load a new address if any of the two lines is active. So the question is, where does this new load address come from? And this is done by the instruction decoder. So there is an additional EEPROM, or more than one EEPROM, which holds the start addresses of the instructions that are implemented in my CPU. And the start address that is delivered to the control logic depends on, of course, the instruction code itself and the state of the flag register. And in my case, there are 8 bits for instructions and 7 bits of flags, so there are a few more flags that I have in my CPU. The instruction register is always loaded as soon as both signals, so say as IL and IC together, are active, and that is always the case on the rising edge of the system clock. So the instruction register will change only on a rising edge of the system clock, and the flag register as well changes only on the rising edge of the system clock, and that means that the address lines of the instruction start EEPROM will only change on the rising edge of the clock. That leads to an instruction start address that is always stable when the clock gets into the falling edge. These two parts put together lead to my design, whereas on the left hand side you see the instruction decoder, and on the right hand side you see the control logic that we discussed before. And since the state of the instruction decoder only changes on the rising edge of the clock, one can be sure that the 12-bit address which is provided by the instruction decoder will be stable at the time that the system clock is falling, and so the 12-bit counter will always be loaded with a stable address from the instruction decoder. Usually all the control logic is way too fast to see, but I made a slow motion video of my control logic, and you see the control lines, which are the blue LEDs on the right hand side, and you can see the microcode step counter, which are the red LEDs on the right hand side just below those blue LEDs. I already mentioned the instruction fetch cycle, which is the code to fetch the next instruction into the instruction register. And this is done in a single cycle in my system, and it consists of 5 active control lines, whereas the first one is a program counter on address bus that the RAM chip knows which address to read the instruction byte from. The next control line is the memory enable, so that the byte from memory is put on the data bus. Then of course IC and IL, both active at the same time, allows writing the byte from the data bus into the instruction register, and then program counter up that sets the program counter to the next available instruction in memory, so that the next instruction fetch cycle can fetch the next byte. Whenever an instruction ends, so whenever the last step of microcode for an instruction is reached, that instruction must also include that IC control line, which jumps back to the fetch code, so to that code we already discussed, that we just discussed. So the fetch code is completely independent of the current instruction, so that whenever the next instruction is read, doesn't matter which instruction is currently active, and that means I only need one copy of the fetch code in my microcode EEPROM. The two control lines IC and IL drive the control logic, and that means there are 4 possible combinations of those 2 lines, whereas if none is active, the microcode step counter will just count up, and if IC alone is active, the step counter will jump to the fetch code, and if both IC and IL are active, Instruction Decoder will load the next instruction byte into the instruction register, and the control logic will load the start address of this instruction into the step counter. But what will happen if IL alone is active? And that means load the microcode step counter to a predefined label, and these labels are set in the microcode and allow jumps in the microcode, and it's implemented on the hardware side the way that there are 2 multiplexers which allow to switch between a byte that is in the instruction register and a byte which is specified by 8 control lines, and these 8 control lines are just reused from existing control lines. So these are 4 control lines for the bus enable and 4 control lines of the ALU function selection, and so it is possible in the microcode to select a predefined address and to load the step counter with an address that the next microcode instruction is stored in. Maybe you noticed the 4 bits for the data bus enablement on the last slide. Just want to explain this because there is only one enablement to the data bus per cycle. So there is only one register allowed to write to the data bus at the same time, and so it is enough to say which of the 14 possible registers is allowed to write to the bus at the time. And so 14 registers can be encoded in 4 control lines named E0 to E3, and there is a list of enablements in this case, and you see there's even a free one, And this is done by just taking the 4 enablement bits and driving them through a demultiplexer, in this case an HCT 154, which maps 4 input bits into 16 output bits, and I use those to control which register has write access to the data bus at a certain point in time. There's a reset switch in my system which is called SW1 in this schematic, and if the switch is closed, there is a positive voltage on this side of the Schmidt trigger, and thus the reset line will be held low, which is the active state for the reset line. So as long as the reset line is low, the system will be held in reset state and will start to run as soon as the reset line gets high again. So this reset switch is debounced via this RC circuit and that Schmidt trigger, and that will also serve a second purpose, because as soon as the system powers up, that capacitor C2 will charge through this resistor, and that means that the voltage at this point will decrease, and at the beginning the voltage will be high enough to be above the trigger value of that Schmidt trigger, and the longer this capacitor charges, the lower that voltage will be, and finally close that Schmidt trigger, and thus letting that reset line go high. And it takes about 200 to 300 milliseconds after power up or after releasing the reset switch to let the system run, and this is time enough to let the system settle and have that reset cycle being done. In my system, it is sufficient to reset the microcode step counter to 0 to reset the system, because at address 0 in the microcode there is some kind of logic, some kind of program that resets the rest of the system. So it clears all the register content. It initializes the program counter, so in this case it reads the address from FFFC and FFFD into the program counter, and then it jumps to the normal fetch code of the microcode to start the program operation. In real life, a reset cycle looks like this. I hit the switch and yes, the microcode step counter goes to 0, and yeah, if you let the switch go, it runs fast. So there is a slow motion version of that video, and you can see the step counter slowly counting up from 0, and then as soon as it hits the first real instruction, the step counter goes wild through, because all instructions have different positions and it switches from instruction to instruction and from address to address. My system also has a simple interrupt logic that allows a program to be interrupted, then deviated to another location, and after that program on the other location has been finished, to resume at the original location. So that allows, for example, to accept data from the keyboard. That interrupt logic is implemented by rerouting the IC destination address. So normally the IC control line tells the microcode step counter to load the address of the fetch code, but in case of an interrupt, a pending interrupt, that rerouting is to a special interrupt code. And that interrupt code will push all the flags onto the stack, then push the program counter onto the stack, sets that interrupt inhibit flag, and loads the program counter with the address of that interrupt routine, which is on FFFE and FFFF. And of course there is an RTI command, return from interrupt, and that instruction does exactly the opposite. So pulls the program counter from stack, pulls the flag register from stack, and then clears the interrupt inhibit flag. So since the program counter is taken from stack, the program will resume at the original point. From the schematic you can get an idea how this works. So there is this interrupt request line that comes in here and is NANDed together with the clock line, but only on the raising edge of the clock, because I want to be sure that the interrupt request is only routed through when the address lines on the address EEPROMs are stable, and then this is fed into this SR flip-flop, so that whenever interrupt request is routed through this NAND gate, it is stored in here, and this line leads to the address lines of the EEPROMs. On the other hand, the interrupt can also be inhibited with this control line, and the interrupt inhibit state as such is stored in this counter chip. I will show that on the next page. The interrupt inhibit logic is meant to prevent the program from being interrupted during timing critical sections like writing to the LCD display or reading from the SD card, and is implemented as a separate register that is just a counter chip, and there is a dedicated control line to toggle between the set and reset state of that interrupt inhibit bit, and this is for just using a single control line. And when this control line is set, the count enable of the counter is enabled, and so whenever the clock pulses and the TI control line is set, the counter toggles the QO bit between set and reset, and this allows with just one single control line to switch between set and unset inhibit state. And to explicitly set or reset the state, so to say to have an set interrupt inhibit or clear interrupt inhibit, those two instructions, set interrupt inhibit and clear interrupt inhibit, are made as conditional microcode statements, so like a jump statement that is dependent on the state of a flag, that set and reset statements for the interrupt inhibit are based on the current II state, so that in case that the interrupt inhibit bit is already set, the set command will do nothing, but the clear command will toggle, and vice versa. The interrupt request is shown by the two LEDs in red on the right hand side in the center, and I type the key on the keyboard and you see the next step switches the interrupt request, and as soon as the next IC control line is active, the program jumps to the interrupt microcode and then loads a new program counter, that's the green LEDs on the top, and then executes the interrupt code. So this concludes the video about the control logic of my 8-bit CPU. As always, feel free to comment, and thank you very much for watching. Bye.